Okay. All right. So now we're recording. Okay. So let's just recap where we were last time. So last time we introduced, which is the whole theory, the many-body theory for the interacting Bose gas, and we derived the spectrum and everything, and I explained to you how it all works. Then we started off with looking at what happens when you raise the temperature of the system. So what I'm going to show you now is that the difference between a Bose-Einstein condensate, which is interacting, and one which is ideal, is that even at zero temperature, not all the atoms are in the ground state. And in fact, in superfluid helium, which is strongly interaction, only about 10% of the atoms are in the ground state. So I'm going to do this calculation. I'm going to spare you some of the details, but we're going to see that the density of the superfluid density is not the same thing as the number of particles in the ground state system. So that's the first calculation we're going to do today. I'm going to then derive for you an equation called the Gross-Pityevsky equation. So we've talked about Landau theory in class. We've talked about it at the beginning. We talked about Goldstone modes and things like this. So I'm going to show you how one can go from this first principles picture to something like a Landau theory, which is called the Gross-Pityevsky equation, which applies at zero temperature, not at critical temperature. And we'll talk about that. And then I'll make some comments about Goldstone's theorem, which are not actually in the notes. I'll just bubble. And then what I'm going to do is just start talking about superconductivity. And I'm going to be very light on superconductivity. We're definitely not going to do all the things that I used to do in the courses at Illinois. If people want a homework exercise as optional, a worksheet to be able to work through and derive the theory of superconductivity using Bogoliubov method, I can give you that. It's super fun. It's quite difficult. It's a long calculation, like the one I did in class. So not that bad, but in principle doable. So I'm going to just tell you a little bit about what superconductivity is, and then introduce to you the Ginsburg-Landau theory, which is what you've been working on in the homework. So that's what we'll do today. On Wednesday, I won't be here, so I will send you what should be the video I want you to look at for Wednesday's lecture. And that'll depend on how far I get today. Okay. Those of you doing the class for credit, if you need an extension on homework, don't hesitate to let me know. Okay. All right. So what we did last time was we defined the depletion of the condensate, D of T, to be the average number of particles minus the number in the ground state divided by number. So it tells you the fraction of particles that are not in the ground state. And since the condensate is what gives you the superfluidity, and the superfluid wave function is given by the superfluid density, rho s, so you might have expected that if I look at the number of particles in the ground state, n0, as a fraction of the total number of particles, n, that would be the same as the density of particle. So the density of the superfluid, if it comes in here, as the spin wave stiffness in the Helicity module, in the Helicity module in the superfluid. So if we saw before, the kinetic energy of a superfluid is given by the gradient of the phase of the wave function. There's a coefficient that comes in here, which is basically times constant times this rho s. And so this rho s, which you think of as the density of superfluid, is also as a stiffness, and that's the thing that you would think is proportional to the number of particles in the condensate. Okay? So I'm going to show you that that is wrong. Okay? And the reason I'm going to show you it's wrong is to underscore the notion that the superfluid density is an emergent property related to the rigidity of a superfluid. Okay, I haven't even started yet, but you've already got a question.
So I guess I just wanted to clarify if that's you have to assume that it's not phase separation. Also.
Yeah, everything is just space. Why'd you ask about phase separation? Well, you mean phase separation between the normal and superfluid parts?
Yeah, exactly.
No. Remember that the whole idea of a superfluid is I have a condensate. The separation is in K space. Okay, condensate is K equals 0. The excited state, the quasi-particles are K not equal to 0. But everywhere in space, it's the same. Okay, now it's not quite true. When you have a quantum vortex line, the core of the quantum vortex line is normal, and therefore, so there are local regions of normal and regions of superfluidity, but it's not like phase separation like you get in material science or in cell biology. Okay. All right, so let's get started. I think it would be a good idea for me just to define what I mean by expectation value. Okay, so we've done it before, but I just want to remind you. So when I write down something like this, what I mean is the 1 over the partition function, the sum over states, which I'll call new, whatever it is I'm trying to take the average of, times e to the minus beta energy of that state. So these are states, and in general, we will use states that are eigenstates of the Hamiltonian. But they can be other things too. Okay, so let's write down then what we mean by the depletion of the condensate. So what I mean by D of T, so I'm going to compute the depletion of the condensate. I need to calculate expectation of n and expectation of n0. So if I write down the total number of particles in the system, it's the number in the ground state plus the sum over the excited states of A, K dagger, A, K. So that's what it is, and these A's are the real, the annihilation creation operators for the real particles. So I want to compute then the expectation value of the number operator, and that's going to be the number of particles in the ground state plus the sum over K, expectation of AK dagger, AK. And so therefore, if I want to compute what is the depletion of the condensate, that is literally just 1 over n sum over K not equal to 0 of the expectation value of AK dagger, AK. So that's just the thing that we have to calculate. Now, the basic idea that we're going to do is to simply transform A into alpha. So there's two parts to it. First thing is transform the A's into the alpha K's. So we're going to go from the real particles to the Bogoliubov quasi-particles, and then the other is we're going to use the Hamiltonian for the A's is going to now go to the Hamiltonian for the alphas. And that was the thing that we worked out last time with these Bogoliubov transformations. Okay, so that's the basic idea. So then what we say is, well, A of K is UK alpha of K minus VK alpha of minus K dagger, and A K dagger is equal to UK alpha K dagger minus VK alpha K. That's equal to minus. One of these is a minus sum. Why there's so many misprints in my notes? I should just use my handwritten notes. Oh, I'll leave it like that. Okay, so if I do that, then what I get is that AK is just this thing. V UK squared alpha K dagger alpha K plus V K squared alpha minus K dagger plus actually minus UK VK alpha K dagger alpha minus K dagger minus UK VK alpha minus K alpha minus K. So that's the that's the expectation value is just plugging in. Now I want to say something else about the chemical potential. Because this will be relevant to what I'm going to do next. So if you ask, if I ask you, what are the chemical potential of the helium 4 atoms? What is that?
Oh, are both of those indices on the final term supposed to be negative K?
Yeah, I think they are. Actually, I don't know. I don't know. No, I think one of them is. So don't worry about it, okay? It's not important, okay? It either is or it isn't. I think
50% chance.
well, no, it's actually a 25% chance that I got it right. I think they're the same. I think this one is probably wrong. So when these notes were typed, not by me, from my handwritten notes, there's a lot of misprints. So you can check in my handwritten notes that you have, I've shared with you before. I will share them with you again. I'll put them on Teams just to make sure you have them, because my handwritten notes are much better than the typed notes. Okay, and those are the ones I've only got with it. So don't worry about it. You don't have to know this algebra. You just understand the basic idea. Okay. Okay. So here's a more important question than the algebra. Okay, the chemical potential for mu, the mu for helium. Okay, so what's its value? Okay, you don't know. You're saying what? Zero? Okay, no, it can't be zero. It absolutely can't be zero. Okay, so what? Okay, what is the sign of it? What? Why?
Well, because we know that they're bosons, the chemical potential has to be negative, because when we derive the Bose-Einstein distribution, it only converges if the chemical potential is negative.
Exactly. Chemical potential of bosons always has to be negative. Okay, go back and look in the notes that I shared with you on how you derive these things. When you derive these things, you see that in order for the series to converge, it has to be mu has to be negative. So mu is always negative. Okay, and the whole point of Bose-Einstein condensation is that mu goes to zero and seems to go to zero at a temperature which is above the zero temperature. So basically, what you know is if I plot mu versus temperature, it has to go like that. And what actually happens is if you don't do the calculation correctly, then what you find is that mu goes like this, and it goes to zero here at Tc. And that Tc is the Bose-Einstein condensation temperature. Okay, and then the paradox is resolved by the fact that you have to explicitly include the zero temperature state in your density of states, and so that's how you calculate that. If you don't know what I'm talking about and you want to know, then send me an email, send me a message. Okay, so mu helium 4 is negative. What about the mu for the alphas? voltage value. Okay, somebody who's not the grader and somebody who's not online. Okay, so what is chemical potential? If you had to explain to somebody on the bus, what would you say? People always ask me on the bus. When I say I'm a physicist, they ask me, tell me what chemical potential means. After I've said that, after I've explained that, and then they ask me how to explain the theory of relativity and stuff like that.
They don't ask about free energy.
Only senators and legislators in Congress ask me about free energy. Okay, so come on, joking apart, what is chemical potential? Right, it's the energy required to add a particle to the system, holding a bunch of things constant. Right, like entropy, for example, things like this. Okay, so all right, so I can think of this as being dF by dN. Okay, so if particles are conserved, then the chemical potential is a value. Okay, now quasi-particles, are they conserved? They're not. What are they made of? Okay, the answer is they're made of stardust, just like everything else. Everything else is made of stardust. You're made of stardust. Okay, but every quasi-particle is a linear combination of all the particles in the system. Right, because I know what alpha is, so then alpha k is, if I want to know what the alpha is in real space, it's a Fourier transform of all the alpha k's, and that then will be a sum over k, it'll be a sum over all the particles in the system. And so every quasi-particle is a collective excitation of the real particles in the system. Okay, so it's made of stardust, but it's not conserved. So if it's not conserved, then dF by dN is equal to 0. If dF by dN is equal to 0, then the chemical potential is equal to 0. So the chemical potential of the quasi-particles is 0, but the quasi-potential of the real particles is negative. Okay, so that matters, because when you do statistical mechanics on the quasi-particles, it's really easy because you don't have to worry about the chemical potential. Okay. All right, so then what do? So you grind away on this, and then the thing that you have to calculate is this. So this is called an anomalous operator, or anomalous Green's function, whatever. And so this thing is equal to 1 over z, the sum over nu of nu alpha k dagger, alpha minus k dagger, nu e to the minus beta e nu. So those are terms that we need to calculate. That's one of the terms. The other terms we have to calculate are just the normal number operator. So those are regular. Okay, so now what we're going to do is we're going to choose the Hamiltonian to be the Hamiltonian expressed in terms of the alphas. So that means that that is equal to just the energy of the ground state, whatever that is, plus the sum over k not equal to 0 of the energy spectrum of the quasi-particles, alpha k dagger, alpha k. So that's what we need. And then when we write down a state like this, so this is N1, N2, blah, 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 and K, like so. And now these are the quasi-particle occupation numbers. Okay, so if I were to compute the expectation value of alpha k dagger, alpha minus k dagger, well, that's going to equal 0. And the reason it's going to be 0 is because the states mu and nu prime are going to be orthogonal, and so if I have this operator here, alpha k dagger alpha minus k, if it acts to the right, it's going to add a particle. So if it acts to the left, it's going to take away a particle. So that means alpha k dagger, that state, acting on any eigenstate, is going to be orthogonal to alpha k dagger acting to the left on any eigenstate. Okay, so make sure you understand. And so in the end, the only thing we have to compute is the number operator. So what it means is that the depletion is 1 over n, the sum from k not equal to 0, uk squared plus vk squared times alpha k dagger alpha k plus vk squared. All I did was just look at the terms in here, and so these terms here, the ones that Frank was asking about, those go away, and then the only terms we have left are the terms that I've written down here. And this thing here is vk squared. What did I do for that one? What I did was I put the alpha to the left of this, so I used the commutator to get out, and that's where this vk squared came from. Okay, any questions about that? Okay, so now let's compute how would we compute the only term that we need there, which is alpha k. So alpha k dagger alpha k is just n k, number of particles in the state k, but these are the quasi-particles. So this is e to the beta epsilon of k minus the chemical potential, but the chemical potential is 0. So it's just the Bose-Einstein distribution for independent particles, but these are independent bosons that are non-interacting, and they have chemical potential 0. So then all I have to do is substitute in the value UK, VK, and epsilon k, and those equal whatever they are, just plug them into here and then do the sum. And when I'm going to do the sum is do the integral. Okay, so that's the basic idea. So now let's talk about the special cases. So first of all, let's talk about zero temperature. Zero temperature is the one that's most interesting. So if I go to zero temperature, then all the particles in the ground state so nk equal to 0, like so, and so then the depletion d of 0 is then equal to 1 over n sum over k not equal to 0 of vk squared. And then I turn this sum over k into an integral, so then it's going to be v over n times the integral d3k over 2 pi cubed vk squared. And the formula for vk is the same one that we wrote down last lecture. So we just have to do that integral. So let me just tell you what are the substitutions that I used to do this integral. So the first thing I am going to do is, let me just write down for you what vk is. So vk squared is 1/2, and then 1 over epsilon of k into h bar squared k squared over 2m plus n u naught minus 1. Okay, that's what we had derived last time. So what are the tricks? So the first trick is, let's define x to be h bar squared k squared over 2m. So that gets rid of that. And then that gives me that epsilon of k is equal to x to the fourth plus 2n u naught x squared. So that's the first trick. Then I'm going to let s squared be x squared over n u naught. And when you do that, then epsilon k goes into n u naught s into the square root of 2 plus s squared. And v k squared goes into 1/2 s squared plus 1 over s square root of s squared plus 2 minus 1. And d3k ends up being 2mn u naught over h bar squared to the 3/2 d3s. So then all you have to do is put that together. So then d of 0 ends up being 1 over 2 pi squared, 2 pi cubed, I should say, n 2mn u naught over h bar squared 3/2 times 4 pi times the integral of 0 to infinity s squared ds s squared plus 1 over s square root of s squared plus 2 minus 1. Okay, aren't you glad I'm doing all this for you? Okay, all right, so then you work it out, okay, and it's not hard to do, but it's, you have to do a calculation, but you can see straight away what the answer is going to look like. So you can do this integral, and I can tell you what the answer is. So this, but the most important thing is this thing over here. This thing over here is just a number. Okay, it's √3 over 2 or something. Okay, and it's finite. Okay, so you can easily work that out. So this is just a number, so we don't care about that. Everything else that we have here, I basically got just by doing this change of variable and following the changes of variables through as I change it in the dimensions. So the only thing I care about is that this is stuff times u naught to the 3/2. That's the only thing that matters. Okay, and in my notes there is what that stuff actually is. Okay, it's a number. Okay, so here's the thing. So the importance of this. So the first thing is that this is not analytic in u naught. Okay, this function u naught to 3/2 does not have a representation in terms of a sum of parallel series. Okay, that's the definition of what we mean by analytic. This is not an analytic function. Okay? I cannot obtain this result by perturbation theory. So you might say, well, wait, that's ridiculous, because this whole calculation is based on perturbation theory. We did perturbation theory in the size of the operators compared to the ground state. We did perturbation theory in the strength of the interactions between the bosons. How come we've got a result that's non-perturbative? So this result cannot possibly be obtained by perturbation theory. Any perturbation theory that you've seen before outside of this class will not be able to compute this quantity. You'll get 0. Okay, so how do we do it? How do we manage a miracle?
Well, at t equals 0, isn't
Hang on,
this?
you already know
sorry,
the
sorry,
answer.
sorry.
You already know the answer because I discussed it with you in office hour,
Right.
right? It's cheating, yes. You didn't know it before you asked me the question. Okay, so somebody in the room. How do we do this miracle? Yep.
Oh, I think I heard what you said.
Oh, oh, okay. What did you say?
Something about it's t equals 0.
No, nothing to do with T. Was
Then I didn't hear what you said.
it? Okay, so what would you say? How do we get an analytic answer from doing perturbation theory?
Having not gone over much perturbation theory ever.
You don't need to know anything about perturbation theory to answer this question.
Perturbation theory is expanding things. around.
Perturbation theory is just a Taylor expansion.
Taylor expansion.
Okay, so and we kind of did that, right? We did perturbation theory in the class. Okay. So so if I'm doing a Taylor expansion, I'm summing up x squared, x cubed, x fourth, blah blah blah, I can't get a result like x to 3 halves. It's mathematically impossible. Well, perturbation theory is just doing a Taylor expansion. So how's it possible that I got a result that's non-analytic? If you did a Feynman diagram calculation, who here likes Feynman diagrams and thinks they're great and wants to do Feynman diagrams when they grow up? I did. Okay, Feynman diagrams would be an epic fail. Okay, that's why I didn't do this by Feynman diagrams.
Does that have to do with something about a region of analyticity?
No, it's nothing so clever like that. So.
Is it that we get infinite expansion, like kind of like a Fourier series where you get lots of different coefficients?
What you're trying to say is, if I sum an infinite series, is it possible to, because I'm summing an infinite series, to get a non-analytic result? The answer is yes. That is a true mathematical statement. It is possible to do that.
What about a Laurent series?
Well, then don't be. I think you're overthinking this. Okay. Look at what we did last lecture. Okay. Flip back in your notes. Okay. Did we do? What is the question you should be asking yourself? Yeah. The front row team can look at your notes. You can discuss with each other. You can discuss. You figure it out.
Maybe it's
No,
because
you've done this class already. You can't talk. You're the great.
I didn't do this class, but fair.
You did this when you were.
I did
You took
I
this
did
time.
Bogoliubov transformations with Dan.
Okay, then do you know the answer?
I figured maybe it's just the fact that we are not in particle space. We're in quasi-particle space.
Expand over the interaction
Yeah. That we did, yeah. So
and the interaction is square root of
the interaction is you. The reason Hamiltonian, you know.
Yeah.
Okay, here's a question you have to ask yourself. Did we actually do perturbation theory? Do we do perturbation theory? No, we didn't. Why? What did we do that wasn't perturbation?
Just assume that the constant of is
Yes, that's true. I could have not done.
also assume that it definitely is not a function.
That's also true, but that was my starting point. It wasn't my perturbation. That was my Hamiltonian.
We ignore some.
Well, you're on the right track. But in perturbation theory, you always acknowledge that, right? You always say, okay, you never do infinite order perturbation theory. If you do infinite order, you wouldn't need to do perturbation theory. So did we do good old honest perturbation theory? Nothing up our sleeves. We roll on our sleeves, make sure there's nothing hidden. Did we do that, or did we do something? Did we do something more tricky?
So in perturbation, we assume that the excitation is thrown at a small number of excitation. You do not expand in the.
Well, kind of, but you're overthinking.
It's not in U dot, but in like alpha.
But that's true. That's kind of true. But did I do perturbation?
It's in the alpha. You
Okay,
ignore
look at the screen. Did I do perturbation here? What?
in the line of the.
That's true. I was pretending to do perturbation. My question is, did I do perturbation? Let's look down. Did I do perturbation? The whole calculation is on the screen. In perturbation theory, I just calculate terms. Did I do perturbation theory, or did I do something else?
But you're just plugging in only the higher order terms.
Well, I didn't omit the high order terms. Okay. High order terms, omitting high order terms, which is quite correct, is what we do in perturbation theory. Is you've got some small parameter, and then you say, well, I'm going to expand in that parameter up to order, x squared or x cubed or something like that, and then I'm going to say the remaining terms are small. Did I do that? Is that what I did here? Look at the screen. What did I do? What did I do differently?
Like you are considering the coefficient of the particle.
I am. And which term?
Now it's not physical and you set it to 0.
Right. This term over here. We looked at this and we said this term is just a constant. This term I know how to interpret it. It looks just like the thing I'm aiming for. This term is yuck. So what am I going to do? So I said, aha, well, remember, I've got two unknown variables, u and v. And I know that u squared minus v squared is equal to 1. That was a condition I required to invert the transformation. And then the other thing I did was I said this term here, let's just set it equal to 0. And then we got rid of the term we don't understand, and we also get the second constraint on the u's and the v's. Okay. Is that step perturbation theory? Definitely not. Okay, perturbation theory, you never have a choice. You just calculate Taylor series coefficients. Okay? We didn't do that. So what we did here by making this happen, we did something that is non-perturbative. That's the step. That's where I cheated you. Okay, there's nothing perturbative about this calculation. The only way to get this result is to do what one of you said. I can't remember who said it. Okay, one of you clever people said, "Oh, we could have just summed an infinite number of terms and got a non-analytic result." It was you. Yes, you can do that. Okay, you can do this by Feynman diagrams or summing infinite number of terms, or you can do it by summing infinite number of terms and using a normalization group to help you do it. And that's the only way you can do that, because an infinite sum of analytic terms, an infinite sum of analytic terms can be non-analytic. Okay, so the only way you can get something non-analytic, right, as those of you who did the phase transitions part of the course last quarter, the only way we can get non-analytic behavior in phase transitions if you take the thermodynamic limit, because you're summing an infinite number of terms, you've got an infinite system size. So you're totally right. You could have done that. This way did that. This trick, you can't see it from here. This trick is equivalent to doing that. Okay, it's fantastic, but it is. Okay, and why it is not obvious. Okay, it took people like 40 years to figure that out. Actually, I would say that people still don't fully understand. Okay, okay. So because how you do this properly by RG and so on, in my view, is really a little bit.
Yeah, for me, how you set that last term to 0 is the kind of the tricky part. Like what the sticking point for me? How do you justify that? Other than it just saying, "Oh, it's small."
I didn't say it's small.
No, I know. You're saying
I said it's identically 0. And I said I'm going to use the constraint on the u's and v's. I'm going to require them to satisfy this thing equals 0. Not that it's small, but it's literally 0. Okay, so how that works? I mean, people are still writing papers on how this trick works. I'm writing a paper on it right now. One of my students, half her PhD thesis is on this trick.
No wonder I didn't get it.
Applied to problems in the normalization group theory and PDEs and turbulence and things like this. Okay, this trick is a very powerful trick. This is why I taught it to you, because it's easy to do, and yet it solves every problem I know. Okay.
Is the impetus for wanting to say 0 because it's that alpha k dagger, alpha negative k dagger plus alpha minus k is like unphysical?
Yes, the reason that we throw up when we look at the term is because we don't know what it means. But here's why we don't know what it means. Alpha creates a particle. A dagger creates a particle. A thing without a dagger doesn't. Okay, so if I look at that term, it violates number conservation. Okay? So I don't know what it means. Okay, in fact, this whole theory is actually, if you want to start thinking seriously about it, you say, wait, how does it make any sense? Because actually the number of particles isn't conserved, the number of real particles isn't conserved, then never mind the number of quasi-particles. Okay, so that's why you have to use the chemical potential. That's why you have to use the grand canonical distribution to write this, because it's a number non-conserving. Same thing is true with the BCSD with superconductivity. And that's also why, well, I'm going to come back to this in 5 minutes when I talk about my comments. Okay, so that's the reason why we say this term is horrible. Okay, and it's amazing that you can get, just by taking the second order term and saying let's make the coefficient of it equal to 0. It's amazing that that gives you the result that you would get going to infinite order by Feynman diagrams or the normalization group and stuff like that. Okay, it's a non-perturbative kind of transform rotation in operator space.
So does that concurrence kind of add weight behind saying that the alpha's coefficient is non-physical, that it's something that wouldn't exist or happen?
It's something with it actually is more subtle than that. It actually can exist, but if I'm thinking in the grand canonical distribution, I don't need particle number to be conserved in any case. Okay, I posted my notes on statistical on the grand canonical distribution in Teams. Okay,
Actually, no, my statement doesn't really make much sense.
well, it does.
At least to me, because I was more asking, because I was thinking that, okay, the term has to go to 0, but we're also enforcing that the coefficient of
The coefficient.
non-alphas.
Yes, the term is not 0.
So
if I count,
doesn't necessarily.
it doesn't have to. It's yes, exactly right. Thanks for the great question.
Impact is,
See, it's like this. We're talking about number non-conservation. Okay, I have a box. I have a bunch of particles in it. Do a calculation. If I seem to violate the number of conservation of particles, you will say my calculation is completely rubbish. Okay? And we'll be right. Okay? Can't do that. Okay? I can see the atoms. I can put them into my atomic trap in most of those experiments. I can see them. He hasn't lost the data.
He always commented.
Close. Okay, so they have to consider. The good thing is that's not what you're doing in statistical mechanics. Okay? In statistical mechanics, you're not doing this at all. In my notes, that's my system. This box, that's what you think is in your experimental lab. This is what's in your calculation. Is inside this dotted area here. And these particles inside here, these are particles flying around. And we're zooming in this, and there's particles coming in, and there's other particles coming out, and so on. Okay? So the reason that the energy fluctuates in this region is because particles are coming in and out. That's why you have a temperature. Because remember, if I just have this box, an outer box, sitting in the room, its energy is conserved. How can you have a Boltzmann distribution? You can't. The energy never fluctuates. But inside this dotted region, the energy can fluctuate. And the temperature is the variable that kind of tells you the Lagrange multiplier to go from thing which is conserved to something which is not conserved. So the number of particles is fluctuating, and the number of, because they're flying in and out of this volume that I've chosen to call my system, the energy is fluctuating because the particles carry kinetic energy. So neither energy is conserved nor is particle number conserved. And that's why when I write down the Gibbs distribution, this tells me what is the probability of finding a system with energy E and a number of particles N. If I'm in some quantum state Ni, this is proportional to E to the Ui this view of the chemical potential. That's the grand canonical distribution. It tells you what is the probability of observing a system of energy Ni given that I'm in a quantum state I. The state is specified by energy and by particle. So when I'm doing calculations, so then if this thing, alpha dagger, doesn't conserve particle number, that on its own is not bad. I told you that it was bad because I knew you would think it was bad. Okay, so this thing can in principle be non-zero. So we made the coefficient of this equal to 0. That was the thing. Okay. We think to call anomalous green spectrums. They can be non-zero. Okay, so a very long discourse. Did I answer? I saw the people who are on Zoom missed it because they can't see the blackboard. But it's all in. It's everything is in my notes online. So did I answer your question?
Yes.
Please say yes, because I want to carry on with the rest of my lecture. If you have any other questions about this, let me know. Okay, so that's the thing. First of all, that so the answer to this question is that the step of setting the coefficient of alpha dagger equal to 0, the coefficient was non-perturbative. Okay, so that's the first thing. If you do this in for the BCS theory, if you want, if anybody wants to look at this, you can do the calculation. What you find is that the ground state energy, or the difference between the ground state energy and the excited state is called the BCS gap, and that thing is proportional to e to the -1 over the number of the density of states of the Fermi surface times the interaction strength, which is the interaction between the electrons in the superconductor. So in BCS theory, this is the energy gap between the ground state and the first excited state. And this thing over here is the density of states of the Fermi surface this thing over here is the effective interaction between electrons. Okay, so this also is non-analytic. Okay, this is why the problem of superconductivity took 50 years to solve, and people who solved it got a Nobel Prize, because you cannot get this by perturbation theory. Okay, and everybody else, including Einstein, Fermi, Feynman, Landau, Onsager, they all tried it using all sorts of clever tricks, which are basically end up being perturbation theory, and they got it, and they never got it. Okay, Bardeen and Cooper Schiefer figured it out, not using perturbation theory. They used a variational method. Okay, we didn't have to do a variational method here. We actually derived everything just from the Bogoliubov transformation. So when Bob Laughlin won the Nobel Prize for figuring out the ground state, or figuring out the state of the fractional quantum Hall effect, okay, he got that from doing variational methods as well, non-perturbative. Okay, all the clever people at Harvard and so on. One of them on the Zoom, right? I delete that. All the clever people in the world who didn't solve the fractional quantum Hall effect, okay, because you have to solve it by non-perturbative means. Okay, so that's the lesson here. That's why I'm telling you this method. Okay, because all right. Okay, let's move on. This is time to move on to the next thing. Let me tell you what the temperature dependence is. If you work out the thermal theory, you can work it out. And in the course I used to teach at Illinois, it was a homework problem. And what you get is this. So you get that's the temperature dependence. So basically what happens is something like this. I plot temperature, and then up here, I'm going to plot look for something in the graph. I want to make sure I get it right. Notes in these notes, but I don't think I can find it. I'll draw it anyway. So if I plot, so the question that we were trying to ask ourselves was: is the depletion of the condensate the same thing as rho n? So here's the answer. So rho n looks like this. Rho n goes like t to the fourth. The number of particles that are not in the non superfluid particles go like that. The depletion of the condensate goes like this. So first of all, there's a gap here, d of 0, and then here it goes as d of 0 plus some number times t squared. So the two things are not the same. And why does rho n go like t to the fourth? Actually, you can work that out quite simply. Again, it's a homework problem that I can show you if you are interested, but that's the reason for that. Okay, so that's what I want to say about the depletion of the condensate. Is there anything else I want to say? Any questions about this? Okay, so I'm going to move on to the next topic. So the next topic is section 3.7.4 in my notes, and this is on the Gross-Pitevsky equation. Okay, so what is our goal here? So the goal here is we want to write down a kind of Schrödinger-like equation. To describe a superfluid or Bose-Einstein condensate and so on. We all like operators and stuff like that, but basically at the end of the day, what we'd like to have is just a differential equation that we can solve. Okay, like the Schrödinger equation and so on. So we want a kind of Schrödinger like equation that can describe the system. And why do we want that? Well, it's very useful if we want to look at spatially non-uniform systems. So usually when you're doing quantum mechanics, we're thinking about systems that are translationally invariant. When we're doing statistical mechanics, that's what we're usually thinking about. I want us to now start thinking in our minds that we're moving towards looking at pattern formation. So we're looking at non-equilibrium phenomena. We're looking at systems like biological systems or artificial biological systems. All of these things are definitely not translationally invariant. And so when you start having things like that, you want to start having a toolkit to be able to deal with non-uniform systems. Now, when you're talking about a superfluid, you may also have a non-uniform system. Give me an example of where we have non-uniform system in a superfluid. And we've talked about it in class. Okay. Come on, answer. Quick, wake up. BC and well, but that's that you could say that, but that's not intrinsically spatially uniform. You just applied an external field. So you could say, well, there's a boundary. So that is one answer, but it's not a very interesting answer. What is a vortex configuration? Okay, there's an emergent state of non-spatially uniform order that emerges, even if I have no external potential. Okay. So we saw that the system has topological excitations, which are vortex lines. They're non-uniform. Okay. So if you're going to try to describe a quantum vortex line by superimposing a bunch of plane wave states, which is what the A's and A daggers destroy and create, that's going to be horrible. Okay, we've got a bunch of plane waves. Okay, formally you can say Fourier series can explain anything. Well, that's true, but it's awful, right? Okay, so you'd like to have a much more simple, compact explanation of what is a quantum vortex line. But then also, like what you said, I have a surface. Then you might say, well, near the surface, the superfluid density is going to change rapidly to 0 or something like this. So you want to be able to describe that as well. So that's why we want that. And so that's why we're going to talk about this equation. And then this equation is going to be, the other reason that we're interested in this is it's some kind of, something like the Landau theory. We've talked about a lot in this class, something like Landau theory, but Landau theory is valid for T around TC. We use it best mostly to describe phase transitions or behavior near there or semi-quantitatively. So, but here we're going to be interested in 0 temperature or close to 0 temperature. So the equation that we end up with will look kind of like Landau theory or Ginsburg-Landau theory, but it's not the same thing, and you'll see why in a minute. Okay, so let's do the calculation. So the basic idea of the calculation is we're going to write down the Hamiltonian for the interacting bosons. In the pseudopotential approximation. And then we're going to use the Heisenberg equation of motion. So we're going to use the Heisenberg representation of quantum mechanics, and we use the Heisenberg representation to write down the equation of motion for the field operators in space and in time. And the last thing that we're going to do is that once we've done that, we're going to replace the ground state by a complex number. So then we're going to say that the ground state operator, so I'll write it like with a hat, so you know it's a field operator, goes into some wave function. So that's a complex number. So that's the basic idea. So let's go ahead and do that. And again, I'm just going to just quickly go through this. So let's write down. So remember, we started off with our Hamiltonian as being the sum over k h bar squared k squared over 2m, ak dagger ak, and then we had u naught over 2v, sum over k1, k2, k3, k4, then ak1 dagger, ak2 dagger, ak3, ak4, and then we had a momentum conserving delta function, so k1 plus k2 equals k3 plus k4. So that's our Hamiltonian. So now we can write it down in field operators. And just to remind you, those field operators were just the Fourier transform of the AKs. So if you go and do that, then so you're going to do that, and we're going to remember that k is the same thing as minus k will go to minus I, h bar k will go to minus I h bar grad. So momentum operator h bar k is just the same as the differential operator minus I h bar grad in quantum mechanics. So then what I get then is that the Hamiltonian is exactly this. It looks like that. So I've got a gradient term, a grad psi squared term, and then I have psi. I have 4 psi's. Why do I have 4 psi's? Well, because in my original Hamiltonian, I have the density at R times the density at R prime times the potential. Potential is a delta function. The density operator is just A dagger A, it's just the number. So I'm going to have 2 factors of rho, so 4 factors of A. This 4 factors of A will turn into 4 factors of psi. So I have a Hamiltonian in terms of these operators, which is quartic. There's no quadratic term. No quadratic term. Okay? Because there's no term that's quadratic in it. So that's the Hamiltonian. Okay, so that's the Hamiltonian. And then I compute the equation of motion. So the equation of motion for an operator psi of r and t, and let me write it as psi like that, so you know this is an operator. That from quantum mechanics is just the commutator of psi of r and t with the Hamiltonian. So all I've got to do is work out that commutation. I know how the psi's commute with each other. The Hamiltonian is just bunches of psi's, so I know how the psi's commute. So I just have to compute that commutator. Okay. So you just have to do it, and here is the answer. You're going to get minus h bar squared over 2m del squared psi plus u naught psi of r and t psi of r and t psi of r and t, and there is a dagger in one of those terms. And another misprinting, but yeah, I think it's like that. So that's what it looks like. And yep, so that's the equation. These are all operators. And then if I write psi hat is equal to psi naught of r and t plus the psi tilde of r and t. So this one here is a complex number for the ground state. This thing over here is an operator for the excited states. Then what I end up with is the equation that I h bar d by dt plus h bar squared over 2n del squared acting on psi is equal to u naught psi naught squared psi naught. So that's the Gross-Pityevsky equation. And you might say, this just looks like the Schrödinger equation. And it kind of does look like the Schrödinger equation, actually. Look, here, I'll write it in a way that makes you think of the Schrödinger equation. I can write this as IH bar d psi by dt is equal to minus h bar squared over 2n del squared psi plus v psi. So this is the Schrödinger equation, right? And the v, I can just read off, is psi naught squared. So it is a Schrödinger equation, but with a potential which is proportional to the density of particles. Yeah. No, well, sorry. Yes. No, you confused me. Okay. So you're right. There should be a U0 in here. That's what you meant, right? Okay. So this is like the potential for the condensate wave function.
So to clarify, in the first equation written in yellow, on the left-hand side, that is the full psi of psi naught plus psi tilde, and on the right-hand side, that's only psi naught?
Yeah. It's another typo.
Okay, thank you.
Thanks. Yeah, exactly. So, okay, so there you go. So what it says is that the particles are seeing a potential that they themselves make. Okay, so this is just like what happens in Hartree theory or Hartree-Fock theory in solid-state physics. Each electron sees a potential created by all the other electrons. So in other words, the interpretation of this is each boson sees a potential created by all the other bosons. And it makes complete sense because the potential that I experience is proportional to how many other particles around me. Remember, this is at the same point in space. This is V of R. Okay, so I'm seeing the potential at that point in space. So the potential depends on space. So the potential I see is due to all the other particles that are in my vicinity, times the potential of interaction between them, which is just this U naught, which is this delta function interaction. So it sees a potential created by all the other bosons. And so you can say, well, if this boson is seeing the potential from all the others, those other particles are seeing the potential from all the others, there should be some kind of self-consistent version of this. So this is a self-consistent potential. Self-consistent meaning that I solve this equation, I not only find what the potential is, I find out what the solution is for psi naught. So this is an example of a calculation where you're doing the calculation in a way that is self-consistent. Particles create a potential, that potential creates the particle density. And that's what this equation is telling you. It's a circular equation, and we want it to be that the density itself is what's given by the solution of the equation. So you end up with a nonlinear equation, and this equation is known as the Gross-Pityevsky equation. So that's what helium people call it. Mathematicians call this the nonlinear Schrödinger equation. It's a really important equation because it governs all sorts of nonlinear processes that come up not just in superfluids, but also in light, for example. Okay, why do I say light? Well, a laser is a kind of Bose-Einstein condensation of photons. And if I want to send a internet signal around the world through a transatlantic cable, that transatlantic cable is a glass fiber. And so to work out the electric field inside a fiber, what I actually have to do is work out the equations for the electrical and magnetic modes. Those equations are non-linear because the particles in the fiber interact with the electromagnetic fields. And the equation you end up with is an equation like this. So lasers are described like this. If you're going to use the internet, it's described like this. Now this equation is non-linear. It has amazing properties. It has vortex solutions. It has all sorts of other topological defects. Okay, and we use it every day. Okay, so that's this wonderful equation. So we're not going to talk more about it, but its uses are to describe quantum vortex lines, to describe BECs in external potentials, and many other things. If you look on the class website, there is the Emergent States of Matter movie page. Remember I've shown you this in class before? And you can see simulations that I did with one of my students on superfluid dynamics. Do you remember? Yeah? Do you want me to show it to you? You have to get out of here. There's an next class coming at night. Yeah, so if you look at that, those simulations were done using a kind of fast version of this equation. Most people use a slow version of this equation. We invented an even faster way of thinking about this. That's what we did. But anyway, so this equation is used for understanding quantum turbulence and so on. Okay, so that's where we'll finish today. I will send around a link. So for Wednesday's lecture, you can go to YouTube and view the lecture, and then I'll see you again, not this Wednesday, and not next Monday, because next Monday I'll also be away. Okay, so you also have another video to watch. Okay, and I'll be on the East Coast giving a talk at a conference on statistical mechanics, the best conference in statistical mechanics in the world, which is Joel Liebert's Rutgers conference, and so I will be there, and so again.